Hydrogen from sunlight and air is becoming one of the most exciting frontiers in clean energy. For decades, scientists envisioned a world where the sun could directly create hydrogen fuel without relying on fossil resources, complex chemical plants, or energy-intensive infrastructure. That future is no longer theoretical. Today, several competing technologies, each following a very different scientific pathway, are racing toward the same finish line, producing clean, affordable hydrogen using nothing but sunlight and water. Some systems harvest moisture from the air. Some rely on nano-engineered catalysts inspired by plants. Others use extreme heat from focused sunlight to split water molecules. And the most established approach still depends on pairing conventional solar farms with commercial electrolyzers. But with all these approaches moving at once, the big question remains: which of these solar hydrogen technologies actually works, and which ones have the best chance of shaping energy systems in the coming decade? To understand the landscape, it's useful to begin with the technology that has captured global attention for doing the most with the least infrastructure. Solhyd. Solhyd represents a fundamentally different way of producing hydrogen. Instead of building a large electrolyzer plant, installing megawatts of solar panels, and constructing a complex balance of plant system, Solhyd integrates everything into a single modular panel. Each panel contains a photovoltaic layer that captures sunlight and converts it into electricity. Behind that surface lies a moisture harvesting material that absorbs water vapor directly from the air. That absorbed moisture enters a miniature electrolyzer embedded inside the module, where sunlight-driven electricity splits the water molecules into hydrogen and oxygen. The panel vents oxygen out harmlessly, and the hydrogen flows into a tubing manifold that links all the panels together. From an engineering standpoint, Solhyd is astonishingly simple. It requires no liquid water supply, no pumps, no compressors at the panel level, no high-voltage power electronics, and no external inverters. If sunlight and humidity exist, the panel produces hydrogen. The appeal here is obvious. Hydrogen production becomes as easy to deploy as solar. While Solhyd pushes the boundaries of simplicity, SunHydrogen is pushing the boundaries of chemistry. SunHydrogen has spent years developing nanoscale, photoactive materials that mimic natural photosynthesis. Their goal is to split water using sunlight directly without relying on a traditional electrolyzer. Recently, they achieved a major milestone by scaling their hydrogen panels to over a square meter in size, while reaching around 9% solar to hydrogen efficiency across the active area. This is important because hydrogen-producing panels have historically been confined to tiny laboratory cells. SunHydrogen's ability to manufacture large-area modules and demonstrate them outdoors has signaled a turning point. Even more significant, they began deploying a 30-square-meter pilot array at the University of Texas at Austin, where multiple large modules operate together in a true field environment. This indicates not just scientific potential but real-world scalability, a key criterion for any technology claiming to be a future hydrogen solution. Although Solhyd and SunHydrogen both call their devices panels, they are built on entirely different scientific principles. Solhyd uses photovoltaics and microelectrolysis. SunHydrogen uses photoelectrochemical reactions at nano-structured surfaces. Solhyd is an engineering solution designed to eliminate infrastructure. SunHydrogen is a materials science breakthrough designed to eliminate electrochemical hardware. One simplifies the system, the other simplifies the reaction. This alone shows how diverse the solar hydrogen field has become, and the broader artificial photosynthesis sector is making headlines of its own. For decades, artificial photosynthesis, splitting water using light-activated semiconductors, has been one of the most promising yet elusive technologies in clean hydrogen. Most prototypes either degraded rapidly or offered low efficiency. Recently, however, a research team demonstrated a module-sized artificial photosynthesis device operating outdoors with over 11% solar-to-hydrogen efficiency. This is one of the highest efficiencies ever recorded for a practical, scalable device. What makes this breakthrough critical is not only the efficiency number, but the fact that it succeeded outside of controlled laboratory conditions. Sun, wind, dust, and variable light conditions have historically crippled photoelectrochemical devices. The fact that new materials and coatings are now surviving the real world means this pathway, long considered futuristic, may enter pilot scale by the late 2020s. But innovation is not happening only in low-temperature or nanomaterial systems. Another area seeing rapid breakthroughs is hybrid solar seawater hydrogen production. A new class of devices combines solar electricity, solar thermal energy, and integrated distillation to convert seawater directly into hydrogen at efficiencies above 12%. This is remarkable because one of the biggest barriers to green hydrogen is water availability. Electrolyzers require purified water, and purification systems add cost, complexity, and energy demand. If sunlight can partly or even entirely handle the water purification step, coastal regions, islands, and dry inland areas suddenly become attractive hydrogen production zones. From a developer's perspective, removing water treatment from the equation can dramatically improve project economics. At a totally different scale, modular electrolyzer systems are transforming how developers think about hydrogen infrastructure. Instead of constructing massive electrolyzer halls, companies are now shipping container-sized hydrogen production units that come fully assembled. Inside these containers are electrolyzers, water tanks, pumps, power electronics, purification systems, compressors, and dryers, all pre-integrated. Developers can deploy a megawatt of hydrogen production simply by placing containers on a pad and connecting them to a solar array. While this isn't as futuristic as producing hydrogen inside a solar panel, it represents a crucial trend. Hydrogen production is moving towards standardization, modularity, and fast deployment. This mirrors Solhyd's philosophy at a larger scale and reinforces the idea that the future of hydrogen may not always rely on custom-built infrastructure. At the same time, hydrogen is beginning to show up in real, practical applications. One of the clearest examples is the installation of a combined solar hydrogen system at a transit depot in Osaka, Japan. Panasonic supplied a system that uses on-site solar power to produce hydrogen, which is then used by a fuel cell to help power transportation operations. This kind of deployment matters because it demonstrates how solar-to-hydrogen systems can support mobility, backup power, and energy resilience at the municipal level. For content creation and course development, these examples show how solar hydrogen moves beyond theory into daily life. Comparing all these approaches with Solhyd highlights important distinctions. Solhyd's greatest strength remains its independence from liquid water. Unlike SunHydrogen, artificial photosynthesis devices, hybrid seawater systems, and conventional electrolyzer plants, Solhyd pulls its water directly from the air. This allows hydrogen production in areas lacking water treatment infrastructure. In many developing countries where water scarcity threatens energy security, this could be Solhyd's strongest advantage. Instead of focusing on efficiency per square meter, Solhyd focuses on making hydrogen production possible anywhere sunlight falls. Scalability highlights another major contrast. Large-scale solar-to-hydrogen systems like PV-driven electrolyzers or solar thermal hydrogen plants scale in huge increments. Artificial photosynthesis may one day scale via manufacturing but remains early. Containerized electrolyzers scale in megawatt blocks. Solhyd, however, scales exactly like solar PV, panel by panel. For small businesses, farmers, off-grid communities, experimental developers, or emerging economies, this democratizes hydrogen production. You don't need 50 million to start. You can begin with a few panels. Durability also plays a major role. Solar electrolysis plants rely on well-understood electrolyzers with long lifetimes. Solar thermal reactors must endure extreme heat cycles. Artificial photosynthesis devices face degradation risk over time. Hybrid seawater devices must handle salt, corrosion, and thermal cycling. Solhyd must ensure the longevity of its moisture sorption material and built-in electrolyzer. But because each panel is relatively simple and sealed, maintenance requirements are much lower than large-scale plants. Replacement becomes affordable. Efficiency is one of the most misunderstood comparison points. Artificial photosynthesis and hybrid systems currently show the highest solar-to-hydrogen efficiencies. SunHydrogen is closing in with large area modules. Traditional solar plus electrolyzer systems deliver the highest industrial outputs. Solhyd's efficiency per panel may be lower, but its system-level efficiency gains come from eliminating water pumping, purification, and power conditioning losses. More importantly, efficiency is only one piece of the equation. Cost, ease of deployment, and site flexibility matter just as much, and sometimes more. Water availability remains the most decisive difference. Solar thermal plants, artificial photosynthesis modules, SunHydrogen systems, hybrid devices, and standard electrolyzers all need liquid water. Solhyd does not. This single factor can determine whether a project is viable. In many regions, the cost of desalination or the logistics of supplying high-purity water outweigh efficiency gains. For coastal regions, seawater-compatible systems may compete, but in inland, arid, or infrastructure-poor zones, Solhyd stands almost alone. The energy transition is now entering a stage where hydrogen production technologies will no longer be defined by a single winner. Instead, different technologies will serve different functions. Large-scale hydrogen production for industrial customers will rely on solar-powered electrolyzers and, in some regions, solar thermal reactors. High-efficiency research will continue pushing artificial photosynthesis forward. Coastal and island markets may benefit most from hybrid seawater systems. Distributed water-independent hydrogen production, small farms, remote communities, small businesses may adopt Solhyd-style panel-based systems. What unifies all these developments is the move toward modularity, flexibility, and adaptability. Hydrogen is no longer confined to billion-dollar plants. It is becoming something that small developers, off-grid users, municipalities, farms, and small industries can consider. As breakthroughs continue, project developers need reliable tools to understand cost drivers, compare technologies, model feasibility, map water requirements, and present bankable plans to investors. For professionals who want to understand and work with these technologies, h2hub.reneweenergy.com offers the resources to get started. Feasibility templates, permitting roadmaps, LCOH calculators, and the Hydrogen Project Starter Kit. These tools are designed for developers and consultants who want to make informed decisions in a rapidly changing landscape. Whether you are evaluating panel-based hydrogen, hybrid seawater systems, containerized electrolyzers, or large industrial hydrogen plants, the goal is the same. Build projects that work in the real world, not just on paper. And with solar hydrogen advancing faster than ever, the next decade will reward those who understand the differences, follow the breakthroughs, and adopt the technologies that match their environment.